Hello again, I'm Jade. I'm going to be talking about Chapel tools, kind of the state of what we have today, and maybe what we'd like to do in the future. I think language tooling is absolutely essential. You cannot just have a compiler and that's it. Your users expect support. You know, a Linux graybeard might just be able to work with Emacs and be happy, but the rest of us want tools. I think the three big ones here are editor support. So VS Code, Vim, NeoVim, Emacs, I mean, just very basic editor support. That's huge. Static analysis, so being able to find bugs before you ever run your code. Static analysis, a linter, is an essential tool for that. And the last one is a package manager. All of the big languages today have package managers because this saves you time needing to rewrite the code and have to manage those dependencies yourself. So think of NPM, Cargo. I think C++ is still missing a good package manager, but it's essential. And the bonus one here is being able to have good debugger support. C and C++ have like the best debugger support ever because that's what the debuggers are built for. When you start to get into other languages, you start to have more problems. This is one of the big problems with Rust, is it's slowly the debugger support is getting better, but it's not amazing. I think the first three are essential. The bottom one is the next one afterwards.
I would say the debugger support is one of the first ones.
I think I agree with you a little bit. I think if you don't have the first three, no one will touch your code. If you have
I can do without editor support. I cannot do without debugger. That's killing me. Sorry, I don't know.
Unfortunately, a lot of universities aren't teaching how to use a debugger, right? Universities don't necessarily teach how to use a debugger, but they do teach you how to use your editor, your package manager, like a linter. But students don't learn how to use a debugger. So if there's no debugger, it doesn't hurt them. I agree. Users expect tools. A language without tools has no users. Full stop. And I've said Rust a couple times. Rust is an absolutely fantastic example here. The whole point of Rust is to interact with the compiler and have it give you good diagnostics to make your code better. Because of that, it's a very tool-first language. The Rust analyzer helps you write your code as you are typing and lets you write good Rust code. I think we can all aspire to be like Rust in this tool space. Maybe not in other things, but in this space, I think we can aspire to that. Chapel has a lot of tools. These are what I would call the classic tools, which are kind of the set of tools that were written slowly throughout the course of the language. And just to kind of categorize the four things I was just talking about, here's where they fall. We have Mason as the package manager. Chapel Viz is a communication debugger. So it will track communication patterns and give you a very visual, GUI view of where communication happens in your application. And then there's basic debugger support. It didn't used to be great. It's gotten better, which we'll talk about in a moment here. And then there's what I call kind of the new age Chapel tools. These are tools that have been written pretty much in the last 2 to 3 years. And now here we finally get editor support with the language server and the VS Code extension, which is built on top of the language server. You have Chapel Check, which is linter, static analysis, and then better LLDB support and a parallel debugger. And so as you can see here on the left, we have a smattering of tools, but as we get to the right, we really start to, goes the screen, we really start to focus in on these kind of key things that users expect. Other stuff is a really great, they're useful tools, but they're not essential to language development. And so in the rest of this talk, I will talk about a handful of these, not all of them. There's just way too many to talk about everything. But these kind of cover the spread of those 4 different areas. So first of all, this is the big thank you to Dino. we've been rewriting the compiler. This is a project we call Dino. All of these new tools, the reason you've seen this explosion of tools is because of Dino. We are building the compiler as a library, so we don't have to reinvent the wheel every single time in a tool. The tool already understands the language and can do smarts about it. I'm not going to talk much about Dino. I'm not the expert on that. That's Daniel. He will be giving that talk in about an hour. But the one thing I will mention is the Python bindings on top of Dino. You really can't have an explosion of tools unless you can actually write those tools quickly. And the compiler is written in C++. We want good performance. But that's not really conducive to fast development. So the text is a little small here, but essentially what this program is doing is it's parsing some Chapel code, and then it's just printing out in pre-order all the various nodes that are in that Chapel code. And you can see here, this is only a piece of the code. It's missing the imports. It's very wordy. Imagine writing a full tool on top of this. Whereas when you can write it in Python, this is the entire Python program that will parse Chapel code and print it out for you. And so this provides an easy-to-use Python interface on top of that powerful C++ library. So the compiler has all the performance, all the power, and the Python library just calls into it. This is how all Python libraries are written, all good Python libraries, I should say. And so this is what is essential to the rest of these tools. Well, most of these tools. That first tool I'm going to talk about is Chapel Language Server. This is what we use to provide editor support to Chapel. It works in pretty much any editor that you can imagine. Pretty much every editor has support for the Language Server Protocol, or LSP. And what this is a generic kind of server protocol that a language can implement their server for. And then if you have an editor that has the client, it can just call into that server and provide various smarts to the language. I think the key features here are go-to definition, so being able to have your symbol in your code and immediately see where it's defined. Being able to see the type, especially in a generic language, being able to see what type you're using. And live errors, right? If the compiler is slow and takes a while to tell you what's wrong, being able to use a language server that tells you the errors as you type is invaluable. And so this tool is what gives Chapel programmers a modern editor experience, and it saves so much time. You no longer are going back and forth with the compiler of, all right, let me compile my code. Doesn't work. Why doesn't it work? And go back to it. I use this language server all the time. I was one of the first authors of this, and it was basically motivated by I'm really tired of not having any information in my editor. And it's taken a few years of work to get to this point, but now I compile Chapel code way less because I have the language server constantly compiling it for me. So this is fantastic here. I have a brief little demo here of this language server. And this is just a short little GIF that'll loop a couple times. And I'll talk about what's going on here. This is just a simple binary search. You probably all know this algorithm. It's pretty simple. There's no recursion here. This is an iterative approach. But what's happening here behind the scenes is there are two calls to this function. One with a custom record called myContainer that has integers, and one with a custom record of myContainer called of reals, or floating point numbers. And so what the language server will do is it will show me both of those instantiations of that generic code, so I can inspect the generic instantiations in my editor, and that's what you're seeing on those two show instantiations. If you look closely, you can see the types change between int and real. Yeah, this is something we borrowed a little bit from Rust, but there's really no other language that can do type hints like this. And it's definitely a very unique Chapel feature and a very unique Chapel editor experience. Yes?
How does it work under the hood?
I'm going to send that to Daniel as so it's calling into the actual Chapel compiler itself.
Yeah.
How the actual Chapel compiler itself works, that's Daniel's expertise.
I mean, if I just speak into the mic, so yeah.
the question was how it works. The general idea is we run type resolution, right? And just like when you compile your C++ code, your compiler will go through and instantiate all the template functions, say if you're using C++. We're doing the same thing. Because we hook into the compiler, we can say, well, here are all these generic instantiations. Let's aggregate them. And then we find the source location of those and kind of tack them on. And once we do that, like the rest is just there, right? It's these instantiations are fully resolved, so you can just display them as normal. I mean, there's a little bit of like language server stuff or like editor stuff to get it to be performant and to like when you're doing all these changes not to be quadratic in time or something. But those are just little tricks. The real key is just to run the compiler, resolve the tools, aggregate them by the thing, and stick them on the function.
And how do you know, like, as somebody is typing?
Well, so
That I can answer.
yeah.
So every time the code is saved, we will re-resolve it. So in this example, I have autosave on, so every single keystroke is a save and is being sent and recompiled. And that really shows how fast this is happening because I can type at a normal speed and it updates that fast. You can also, turn off autosave, and every time you save, it'll refresh. Right.
And one of the things that it does in particular is it uses something called a query-based architecture, where it remembers as much information from the previous compilation as possible. That's why it's so fast to type, as opposed to running the compiler, which is slow. Yeah,
Yes.
so it does the least possible work to recompute the results.
Really cool.
Yeah, this is game-changing for writing Chapel code. The other thing I want to note here is the error messages, which we'll see in just a moment. As soon as I write a bug here, you immediately see what's going wrong. This is something that might be hard to find if you compile it at the command line, but in the editor, you immediately see exactly what lines you're supposed to look at. This is just unparalleled editing experience. As far as what we want to do next with the language server, for the most part, it's really done. As you can see, Daniel's laughing. It works and it's fantastic. The more improvements that can happen now is improving the compiler's resolution ability, being able to resolve more Chapel code. Right now, that front-end compiler can resolve most Chapel code, but not all Chapel code. So that will allow us to have more information. We'd also like to expand that generic instantiation feature to other parts. Right, that was just a function, but what if you have a generic record or generic class and so on? And also, better support for large projects where, big scales. But pretty much, this is a fully featured, polished tool that just kind of works in your editor and accelerates development. So talking about Chapel Check, this is also a tool that will run in your editor. And it's a static analyzer, a linter, that looks for anti-patterns in Chapel code, both from a style perspective, but from a bug fixing perspective. When, if you're new to Chapel, you might not know that something is bad or that there's a better way to do it. And so this can suggest that to you. So here's one example. In Chapel, a co-for-all loop creates a task per iteration. So if you have a nested co-for-all loop, you are creating a task per iteration. So you are going to end up with way too many tasks and overload your machine. And so the linter can see this and say, nope, don't do that, and warn you about it. And as you can see here, I've hovered over this kind of lint warning, and it tells me, lint rule nested co-for-all is violated, and it gives me a little link. And what that link directs me to is a documentation page that explains exactly why that's wrong and what you should do instead. And so this kind of feedback really helps users learn about the language, avoid common pitfalls, and write better code. Yes? Whoop.
So I don't use the Chapel check myself, but nested co-for-alls is also a common pattern where you do like multi-locale, multi-parallelism.
Yes.
Do you avoid giving this warning, or do you also issue a warning in that case?
So this, and you can almost see it here, this specific rule is disabled by default because what it's looking at is the patterns in the code. And so there are some cases where it's actually okay, and we don't want to warn, but it's a little too overeager. And that's actually something I'll get into in the future work. One that,
I don't know
yes.
anything about chapel, but in there, this kind of very huge amount of parties can be good for GPUs. Right?
So in this case, the code-for-all loop is not going to spawn off GPUs. But what's happening here is because like every single one of those iterations of the loop is a new thread.
Okay.
And so it's not just that like each iteration, like some of them are sharing threads, like this is 10 threads and then 10 threads per thread. Okay. So that's 100 threads, it's way too many. Which is why it's bad here. On a GPU, it's a different story, but code-for-all loops don't map down to GPU kernels. Okay. The other linter rule that I'm showing here, this is also about it's sort of a style, but it's a potential bug. In Chapel, everything is in curly braces. This is not a white space language, but there is a little helper called the do keyword, which you can see at the end of that loop, that lets you write a one-line block without the curly braces. But someone who's inexperienced in Chapel might not understand that pattern fully, and they might try and indent their code and expect it to be inside the loop. We can completely detect that in the linter and warn you and say, hey, this is misleading. It's not actually a part of the loop. And this is not something the compiler can do because it's just kind of white space, but it's something that a tool can absolutely warn about. And so in this case, not only does the warning show up, but we can actually automatically fix that for users. I don't have a GIF here, but if you click that, apply fix, it will automatically unindent the code and fix code for users. And this can be run both from your editor, so the editor you can interactively fix it. You can also just run it from the command line and say, fix all the errors you can. So that is pretty cool. What's next? We can always add more lints. There's more style that we want to codify into this. The other thing is that this is fully extensible, and it's all written in Python. In about 5 lines of Python, you can write your own custom lint. So if you have your own custom style you want to enforce, you can just write a quick little Python file and enforce your own custom lints. We'd also like to do more static analysis, beyond the syntax. So that's where that nested code-for-all comes in that Engin was talking about. And really looking for bad communication patterns where we can warn and say, hey, there might be a better way to do things. If you write it just slightly differently, you'll get better performance. And that's something that, as the type resolver gets better, we'll be able to do a better job of. So I've talked a lot about ChapelPy-based tools. This is all compiler tools. The next one I'm going to talk about is Chapel's package manager, Mason. It's inspired by Cargo, if you've ever used Rust. So frequently when you're writing Rust code, you never actually invoke the Rust compiler. You just invoke Cargo. Mason has a similar idea. It's a much older Chapel tool. I think it's about 8 to 10 years old. But we've started to give it a lot more love and attention recently to really try and grow this tool. We're doing a lot of major refactors to rewrite this for kind of modern Chapel. As the language has progressed and this code has kind of gotten left behind, so we can kind of update it to be more parallel, be easier to read, easier to maintain. And as a part of this, we're writing a lot of tests. Some new features coming in here. One of them is being able to build non-Chapel code. So if you saw my demo this morning, or this afternoon, I would run Mason build, and it would not only compile all of the interop code that I was using, but then it would compile the Chapel code for me. So that was kind of a one-stop shop tool. I don't need to make there's make files behind the scene, but I don't need to invoke those make files. I just say Mason build and everything happens. We've also added significantly better documentation, making it much easier to get started with this. We've started to kind of fill out the package repository and add more packages. And also just kind of in general, subtle quality of life improvements, like being able to specify a list of compiler options rather than a string. So, just kind of, not big features, but, small things that really make it easier to use. There's a lot more work to be done here. We want more Mason packages. This is a small bit of the repo that has all of the Mason registry packages. We've been, I think in the last month, there were 3 or 4 new packages. So it is starting to grow a little bit faster. We want to get better built-in Mason tools. So right now, Mason has built-in unit tests to write unit tests for your package, but we want to provide benchmarking utilities, better debugging utilities, and we want it to be able to function just like cargo, npm, pip. So if you write a Python or if you write a command line tool in Python, you can pip install it globally, and then you can just use that tool. We'd like to be able to do that with Mason as well, because if you can do that, you can then write command line tools in Chapel and have distributed command line tools just installed like that, which would be really, really great. Any questions about Mason before I go on to new debugger support?
One thing that I will add, if you said it, moved on a little bit too quickly, Mason is implemented in Chapel too.
I was going to ask about it.
Yes.
It's implemented in Chapel.
Yes.
So we have like unit testing, for example, that runs in parallel that is using for loops in Chapel and stuff like that. So we benefit from parallelism too. So it has the potential to be a very fast parallel package manager.
Yeah.
Compiling Chapel from source, like the way you would do it in Rust, is previously the first version of Rust was written in OCaml, and then they wrote it again in Rust. So you use an older version of Rust to compile newer version of Rust. Is that similar to Chapel?
So Mason is written in Chapel, but the Chapel compiler is written in C++.
Okay.
We haven't rewritten it in Chapel. We'd like to. It's kind of a nice. Brad, one of the language founders, described it as like a feather in our cap. It's really cool, and we can say we can compile everything with Chapel. It doesn't give us anything, right? It's not a new feature, so it's not something we prioritized.
But one thing related that Jade and I sometimes discuss is building Mason with Mason.
Yes.
So Mason is not a Mason project right now. It's just a standalone project, but it could be actually a Mason project, which would apply the same thing. Like you should use older version of Mason to build the new Mason. So I think we want to get there.
Yeah, that's definitely. We've had a lot of conversations about being able to do that. Anything else? Okay. So on to debuggers. So I'm mostly going to focus on the new parallel debugger tool, but most of this is backed by better support for single locale debugging with LLDB. There's long been support in GDB and LLDB, and it worked. It didn't work amazing, but it worked. And essentially, you were debugging the Chapel code in terms of like generated C code. So it was best to debug if you actually understood what the compiler was doing. So if you're a compiler developer, that's great. If you are just a Chapel developer, you know nothing about the compiler, it's not so great. But we've made a lot of work in making this a better experience, both on that single locale front, but also in the multi-locale front. And that's where Chapel Parallel Debug comes in. To be able to debug multiple locales, essentially you need to debug each individual node by itself, but together as one. And previously, the best method was to export a bunch of windows, one for each node. So if you have two nodes you're going to debug, you have two debugger windows open that you have to control both nodes from that debugger. That's fine for two nodes, but once you start to scale to 8 nodes, 16 nodes, that gets a little unwieldy. It also means you have to be able to X forward from your machine, which doesn't work so great if you maybe are on an HPC system that doesn't let you X forward. So that's where Chapel Parallel Debug comes in. It gives a much more unified debugging experience for multi-locale code. You essentially need two windows, no matter how many locales you have. You have one window where you launch your program, and you launch it in debug mode. And then in another window, you attach the parallel debugger. And then you can just step through and debug the code. And you are essentially, if you've ever debugged like a parallel code with multiple threads, and you can inspect multiple threads, this parallel debugger adds another level on top. So you have multiple locales that you can inspect and multiple threads within each locale you can inspect. There are industry-grade tools that do this. GDB for HPC is one. I think there's a parallel view, something like that. It's an HPC tool that you can use. They're paid tools. They're not open source. This is open source and free and works with Chapel. And so kind of as a nice screenshot of this, over on the left, we've got some distributed code that we're going to debug. I'll just explain it a little bit. What you've got here is the third line, you're creating a distributed array. That's array. And then on the fourth line, unfortunately, there's no line numbers. Just come over here. All right. I'm assigning array equals array.domain. I'm initializing it to basically 1, 2, 3, 4, 5, 6, 7, and so on. I'm then going to loop over all of my locales, move to each locale, declare a locale private variable, which is my var, and then I can copy a slice of that array. So this is not a referential slice, it's a copy, but I can copy just my local slice and then print it out. Over on the right here is my actual debugging session. So up on the top, you can see I'm moving on 0, so to locale 0. And this is very similar to Chapel code, where you can use an on clause to move execution. In the debugger, you can do the same thing. I use F for the frame command to see, where I am in the call stack, and it shows me, hey, I'm at my breakpoint right there. I can then, just inspect my Chapel variables, so I can print out that slice, and it just prints a nice clean array interface. Previously, you would see the internal array implementation, which does not look like that, but now it nicely prints for you. I can continue execution on locale 0, and then you see here at the bottom, I can move to locale 1 and do the exact same thing. Right? So these on commands let me switch between the different threads, just like the thread select command, if you're familiar with LLDB. And because of that, everything happens in one kind of window. And like I said, you can expect different state. So my slice is one variable in the code, but on different locales, it has different state, and you can see that in the debugger. What do we want to do next with this? I mean, that's already pretty great. It can get better. In general, we need better debug information for Chapel. This has already gotten better in the last 6 months or so. But the better information we have, the better debugging is. And kind of bulk actions. So being able to say, on this set of locales, do this thing. That's something that's kind of still future work. It's not that hard to do. We just haven't done it yet. And it would be kind of nice to generalize beyond Chapel. Like I said, there are parallel debuggers out there that do this sort of thing, but they are all industry paid tools. This is totally open source and built for Chapel. It would be cool to generalize this beyond Chapel. And maybe there are other communities that are interested in this kind of thing. And if there are, I would love to chat with you. Because essentially this is just LLDB and orchestration of LLDB. It's not really doing anything too fancy. It's not that crazy, but it's also open source and totally free.
Can you connect to the different instances?
So this is using the GDB remote debugging protocol. So essentially it's a protocol that was implemented for like debugging embedded devices or like debugging kernel launches, like OS kernel. That's what it's kind of built for, to debug one machine from another machine. But there's nothing that stops you from doing multiple of those in one session, and that's really all this is it's one session of LLDB that says, okay, connect to you, connect to you, connect to you, connect to you. Let's all go. So it's not terribly complex, but it's effective.
I don't see a reason why this wouldn't work with MPI.
Right.
I would be very interested. I don't like GDB for HPC.
I don't either.
I've never been able to wrap my head around it.
So I mean,
Very user friendly. So it's having something maybe because yours is based on LLDB, that makes it already a little more useful.
yeah,
I would like that.
yeah, I should definitely connect and talk about that.
How much dwarf information do we put in the executable for this to work? Because that might prevent the MPI to use it, right?
So there's not special dwarf information that we do for parallel debugging. Essentially, it's the same dwarf information for single locale as multi-locale. Really, all the and I'm like, there's maybe a couple hundred lines of like Python LOD calls that make this work. So it's not like super complex and hard, and it doesn't rely on built-in like compiled languages. The one thing it does rely on that's special for Chapel is Chapel has built into the runtime, instead of launching the application, it says, nope, you're going to launch inside of a debug application, and you're going to stop, and you're going to wait for LLDB to connect and say you need to go. So something like that would need to happen for MPI. You would need to launch, instead of launching each MPI application on each node, you would need to launch inside of LLDB on each node and have it immediately stop and say, wait for someone else to connect to me. And I think you can hook into MPI run and do something like that.
It'd be interesting to see if the tools working groups are interested in
Yeah.
working on debugging interfaces for that.
Yeah, and like as you said, GDB for HPC is quite painful, and is also quite tailored to MPI, and doesn't work very well with other things. There's been people at HPE who have run Chapel with GDB for HPC. I wasn't able to replicate it, quite honestly, and so that's kind of how this tool came about. All right. The last thing I'll say here is just there's kind of other tools that we would love to see. My kind of top two right here is an auto formatter and a profiler. The auto formatter, I love auto formatters. They're wonderful, especially when you're working with multiple developers who all have their own preferences and how they write code. You end up having the diff go back and forth and back and forth. So being able to enforce that consistent tooling, even if everybody doesn't agree that it's exactly perfect, right? It's consistent, and consistency is really important. The other one is profilers. This is really important. It's kind of the next step of debugging. There's correctness debugging. There's performance debugging. Chapel already works with standard tools like perf, Linux perf, and HPC toolkit. But there's a little bit of manual work that's required to do it. And we'd like to kind of make these integrations a little bit better for users. And last thing, kind of for tooling, is just in general language migration and interoperability. So one tool I didn't talk about in this presentation is C to Chapel. And what C to Chapel does is it auto-generates essentially a Chapel header file for your C code. Excuse me. So you take a C header, you run it through C to Chapel, and you get the equivalent Chapel extern functions. So it's not rewriting your C code, it's just allowing you to call your C code. And it's pretty basic wrappers. We can make that better. Can we kind of help that tool do more smarts so that it's not just kind of a blank basic wrapper that you then have to tweak? It's something more fancy. And can we just like rewrite your code completely? Can we take a Fortran code and one-to-one translate it to Chapel? Can we take C code and one-to-one translate? This is something where there's kind of multiple approaches we can take, like a very mechanical transformation of this becomes this becomes this. But this is also something I think that LLMs and AI have potential to really make this a very powerful migration tool. And with that, that is my talk on tooling. There's lots of ways if you have interest in developing these tools, working with these tools, want to hear more. There's lots of stuff on here. And with that, thank you all very much. Any questions? Did I go over time or under time?
I think you did overtime.
15 minutes over time.
Oops.
You have to buy HPE.
I can do that.
So can C to Chapel wrap the Fortran functions too? Like I guess just wrapping would be quite useful.
So if you have like a header file, like a C header file for your Fortran, yes. But just like raw Fortran, no. I think that is something that Daniel has done some work on as far as like mechanical, like transformation of Fortran, completely rewriting Fortran functions into Chapel. But as far as generating, I think the more powerful thing is being able to have a wrapper which we don't generate, but I'll let you go, Daniel.
Yeah, so Fortran lets you, so if your Fortran code is declared as bind C, which is like, generating C compatible code, there's also a tool to get the Fortran compiler to generate a C header, which you can then get Chapel to recognize. So from there, relatively simply, you can get a forward declaration in Chapel of your Fortran code and call it from there. It's the generation, I think I'm relying on G-Fortran, like G-Fortran can generate that. So I've had decent luck with that without having to translate anything. But you do need to declare Fortran code as like bind C,
Which that's a requirement for Chapel anyways, because you need the C calling convention to be able to interrupt.
What's the consequence of calling C code from Chapel? Does it have any negative impact on?
I mean, you have the same kind of foreign function interface problems you have anywhere. Of you might miss out on maybe a little bit of inlining. I mean, that's a problem you have no matter what. But other than that, I don't know that there's that many downsides really. Like it's just code. It just works.
And like historically, we've been emitting C code. It's not the default anymore. So if you think of it that historical background, it just all becomes C at some point. So it just everything meshed together.
And if you go a step below, it all just becomes assembly at some point.
Right. I mean, well, if you go one step up, it's all LLVMIR at some point. Could you work with that?
So there is, and I haven't showed it here, but there is a way to literally embed your C code in your Chapel code in the same file. And in that case, that C code gets turned into LLVMIR that is then embedded with the rest of Chapel. And there is no overhead in terms of that function call for an interface because it's all one program that's optimized together. That does require the code to be written in the same file, so it's not as useful for like the interrupt scenario. But that there is that potential there.
If I were to, can I compare Chapel with LTO?
So Chapel is a whole program compiler, so all compilations are LTO in a sense.
Okay, so but if my library is my C library is a fat binary that has,
Then you can do LTO on the final.
it would pull that in as well.
Yes. It should.
We just use the standard linker, right? So
Right.
as long as the standard linker can use LTO.
Right. Which Clang does by default. So. Yeah.
How big's the community?
I think I'm gonna let Engen answer that question.